Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy them. So check out Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. Go to dataengineeringpodcast.com/Linode today to get a $20 credit and launch a new server in under a minute. And go to dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And don't forget to go to dataengineeringpodcast.com/chat to join the community and keep the conversation going. Your host is Tobias Macy, and today I'm interviewing Fabian Hueske, co-author of the upcoming O'Reilly book, Stream Processing with Apache Flink, about his work on Apache Flink, the stateful streaming engine. So Fabian, could you start by introducing yourself?
Yeah, first of all, thanks for having me. My name is Fabian. I'm an Apache committer and PMC member of Apache Flink. I'm also co-founder of Data Artisans, which is a company that was founded by the original creators of Apache Flink. And what we're doing is basically spending a lot of our time on developing and fostering Flink and its community.
And do you remember how you first got involved in the area of data management?
Yeah, so that's actually a while back. Like when I started my career in IT, I was taking part in an education program with IBM Germany. Half of the time there, I was studying at a university, and the other half I was doing internships at different departments of IBM. And for one of these internships, I had the chance to visit the IBM Almaden Research Center in San Jose, California. And there I was working with researchers in the data management department. So back then it was DB2, the relational database.
And so can you give a bit of an overview about what the Flink project is and how it got started?
Yeah, sure. So that's actually a bit of a longer story. So the roots of Flink date back to 2008, 2009. So when I was about to finish my studies, my former advisor from IBM Almaden called me and asked me whether I'd be interested in joining him and becoming one of his PhD students. He was just about to become a professor at Technische Universität Berlin in Germany. Yeah, I agreed to that, moved to Berlin, and in the first year, we basically in the first years, we got a funding for a research project for data management in the cloud. And yeah, we started to build a system back then with the goal to combine the best properties of Apache Hadoop and relational database systems. So back then there was like a debate going on that Hadoop is a major step backwards because it's kind of like from relational database systems point of view, kind of dumb, however, very scalable. So what we built with our system was basically a system that had a kind of like a data flow programming API, similar to what Spark and Cascading and all the other APIs had, and also what Flink has today. And the system was a distributed scalable system capable of processing arbitrary data. So basically much like Hadoop with user-defined functions like a map function that would do whatever you wanted to do. But it also featured an optimizer and an execution engine that was very similar to what a database system was doing internally, like including the way that database systems do their memory management, and also including algorithms like hybrid hash join, for example, that are work in memory and then gracefully spill to disk in case memory is not sufficient. Yeah, the system was called Stratosphere because it was data management on the clouds. And in 2014, we donated the code base to the Apache Software Foundation, and it became Apache Flink. Yeah, since then, Flink changed a lot. Today, Flink is rather known for its stream processing capabilities than for being a batch processor, which is still true. So all these things still work. Yeah, so what is Flink doing? Flink is a distributed system to perform stateful computations over data streams. And the Flink project aims to address all types of stream processing use cases. And we see streams in their broadest sense, which means that it includes bounded streams, unbounded streams, live data, recorded data. So basically, live streams and also batch data. Flink scales to thousands of nodes, can maintain terabytes of state, and also we have enough users that process trillions of events per day.
So there are a lot of things in there to unpack. To start with, one of the things that I'm curious about is the ways that state is managed in the cluster and within the computations, because particularly for unbounded streams of transactions, statefulness, I imagine, can get quite complicated when you're processing in a distributed fashion.
Yeah, so Flink maintains all the state locally on the local machine, so there's no central entity like a database where we would do distributed transactions to. So all the computations are distributed. So you have, for instance, like something similar to a map function running distributed in your cluster. On each of these nodes that runs the map function, there is something that we call a state backend, and this is like a pluggable component in Flink. So you can configure this the state backend to manage the state on the heap of the JVM. Flink is implemented in Java, so you can have in-memory speed there, however, being bound to the size of the JVM. Or you can plug in a state backend that is based on RocksDB, which is like key value store that is writing data to disk. So you can also manage much more data by writing it to disk, of course, with a little bit higher latency there. So all the state is always locally managed. So the functions have local access to the state, which is very good for performance. But then again, this is, of course, a challenge when it comes to fault tolerance, because on distributed systems, things go wrong all the time. So your process dies or the node dies. And for that, Flink has a mechanism to do consistent checkpoints of this state and is able to load that data, basically reset an application and load the data from the checkpoint into the application and then continue as if nothing ever happened.
Flink, as you mentioned, has been around for a number of years now, and there have been a number of other streaming systems that have been built up in recent years from various different companies trying to suit different use cases. So I'm curious where Flink fits both in the context of other streaming systems and also into the broader modern data landscape, particularly given the fact that things have changed quite a bit since you first began working on it.
Yeah, sure. So yeah, as you said, there's a bunch of stream processing software and systems out there. So first of all, what is Flink not? So Flink is not an event log or a system to store your stream or to distribute a stream. So it's not similar to like the Kafka event log or Apache Pulsar, for instance. So it's not meant for storing and distributing streams. It is a processing engine, and it's much more similar to Spark and also Storm to some extent. So it's similar to Spark because it has also the batch processing capabilities, similar to Spark. But the Flink project today is focusing much more on stream processing and is an event-at-a-time stream processor. So we're not doing microbatches as Apache Spark, for instance, but we're processing events one by one without scheduling new microbatches. Compared to Storm, which is also like event at a time architecture, Flink added its stream processing capabilities much later and provides event time processing. I guess we'll talk about that a bit later. And also better consistency guarantees. So exactly one state consistency and higher throughput. Storm is somewhat bound by its fault tolerance mechanism when it comes to high throughput.
And what are some of the primary use cases that end users of Flink are leveraging it for?
Yeah, so I said before, Flink is like trying to capture the full area of stream processing. So what are the kinds of stream processing applications that we see people running Flink for? So one of these use cases is data pipelining or low latency ETL, like moving data from one location to another with low latency. This is a very, very common use case, although probably not the most advanced, I'd say. Streaming analytics is, of course, another big issue. And then there is also this area of event-driven applications, which somewhat go in the direction of microservices. So you're building an application that receives events, usually from an event log such as Kafka or Pulsar, And then this application runs some business logic that reacts to individual events. So it receives an event and then performs some kind of business logic, puts some of the information into its state, forwards some information, maybe a notification or an event that is processed by another application a little bit downstream. So it's like these event-driven applications are a little bit more like applications that would have been designed with a separated, like business applications that would store data in a relational database. So they have a little bit more like the transactional nature of stream processing, where the analytics is, of course, more analytical.
And in order to be able to support these low latency processes, as well as scaling to large numbers of nodes and large volumes of data, I'm wondering if you can discuss a bit about the underlying architecture of Flink and how that has evolved over the years that you've been working on it.
Yeah, so I mean, Flink is a distributed system, so it follows the classical master worker pattern here. I said before, it's mostly implemented in Java. Some parts are also in Scala, but those are mostly APIs. Flink processes data as data flows, so it's like distributed parallel pipelines. So the data is like distributed, processed by these individual operators, and whenever you need to organize the data by key, it is like hash partitioned and then shuffled over the network to the corresponding node that processes that key. On the for the network shuffling, I said we're following like this event at a time processing, which means that we are of course not sending individual events over the network, but we're always like collecting them in a network buffer that we then ship for better throughput, of course. But the data is like eagerly pushed forward. It's not like in a batch engine that would first collect all the data and then tell the receiver to download to load some of the data. But instead, the data is like eagerly pushed forward from the sender to the receiver. On each receiver, I already briefly talked about the state backends. The events are received from the network buffer, they're unpacked and then forwarded into the user functions. And then state is usually also sharded per key in Flink. So each or the state of each key is only processed on a single machine. So the events are routed to the machine that is responsible for the key. And then it's like the state backend's responsibility to look up the right state for this key. So I said we have the state backends for the JVM heap. So in that case, the state is accessed, read or written by putting the Java objects directly into the heap, or the data is deserialized and serialized to get it out of or into RocksDB.
And given that you have been working on and evolving this project for a number of years, are there any aspects of the current implementation that you would do differently if you were to start over today and didn't have the weight of legacy behind the existing infrastructure and APIs and design patterns?
Yeah, sure. So as I said, so Flink started as a batch engine, and like the streaming was added later. Well, to be fair, like most of the execution was always streaming, or like streaming from the start. So I said before, we've designed Stratosphere back then, and like later Flink with database principles in mind. So the research group that I was working on at university was a database research group. So we had like naturally like a database background there. And database systems also tend to have this pipelined processing model where like the data is always pushed from the roots of the processing of the execution plan towards the root node, so eagerly pushing forward. And we had like the same design right from the start. So the network layer was always like pipelined. On top of that, we built like basically two separate engines for batch processing and streaming, and also like two different APIs. So in Flink, they're called dataset API for the batch processing, and the stream API for the streaming. And yeah, so if I would like design things new or starting from a green field, I would try to have these things more tightly integrated. So Flink is going to that direction. So that's like one of the points on the roadmap to unify batch and stream processing. But yeah, as often it's a bit harder to change something that is already there than like starting from a green field. Like this tight integration of handling bounded streams and unbounded streams would be nice.
And in terms of the bounded versus unbounded streams, are there differences in terms of how end users need to think about the way that they approach those problems for their own processing?
Yeah, well, yes and no. So Flink has, besides like these APIs that I mentioned, the dataset and the data stream API, Flink has also two relational APIs, which is like SQL and a link style table API. Link is like stands for language integrated queries. So this is basically a way to not define a query as a string in a programming language. So when you write a SQL query, you typically like compose it as a string in a programming language, but have like the query operators embedded in the programming language. Like you have some kind of a table object, and then you call select or group by on this with a method that is embedded in the programming language. So this is like link style, and this is like how the table API of Link looks like. So we have these two relational APIs, and these two are unified APIs for batch and stream processing. So depending on what kind of like how the data looks like that is processed, how the tables look like, if those are like bounded batch tables or unbounded stream tables, the query is compiled differently. Like in the batch case, it's compiled into a data set program, in the streaming case into a data stream program. But the semantics of both programs is exactly the same, regardless of whether the data is read from some kind of persistent store or whether the data is like live arriving. And the principles that these APIs here, or the streaming APIs, the stream processing for these relational APIs follows is the one of basically maintaining a materialized view. So the query is like a continuous query, and then as more data arrives, the result is continuously updated. So this is like the part where users don't really don't have to worry that much about the difference between bounded and unbounded streams. But then again, there is like the data set API and the data stream API, which clearly separate batch and stream processing.
And for unbounded streams, there's the possibility for events to arrive out of order in terms of the timestamps associated with those events, or for different machines that are originating those events to have different clock alignment, which can cause some difficulty in terms of event ordering. And you mentioned that Flink has native support for being able to support some of these out of order events or delayed events. So I'm curious how that functions and some of the ways that that simplifies the work of the end user who's trying to process these event streams.
Yeah, so Flink supports event time processing. And what we basically mean by that is that data is not processed with respect to the local wall clock on each processing machine. So let's take, for instance, the example of doing a simple windowed count per 10 minutes. So if we want to like count how many events our application sees every 10 minutes, then there is like different ways to do that. So the first question here is basically, how does the machine measure what 10 minutes are? The easiest way is, of course, to always look at the local machine clock on the data processor, and that will give us some time. And after 10 minutes, we can say, okay, now 10 minutes are over. I can compute the count, and I just emit the number of records that I've seen during the last 10 minutes. Of course, this is not very precise and not non-deterministic, because it depends on the speed at which data is ingested, is there back pressure in the application, how fast is the machine that is doing my computation, and so on. So looking at the machine clock is sufficient for some applications if you only want to have like approximate counts. But if you want to need precise and deterministic results, then this is not sufficient. So this mode is called processing time in Flink. And then there is event time. And in event time, each event has a timestamp associated with the event. So as you said, this timestamp usually encodes when this event happened or when an event was produced. Yeah, so we have now timestamps on each record, so we basically know when each of these events happened, and like having the time in the record is already good. But now the question is, how can we, like, when do we know, or how can we know when we can, like, close a computation? How can we be sure that no more record is arriving with a timestamp that we would need for this computation? And Flink uses the concept of watermarks here. So this is like very similar to what the Google data flow model is doing. Or basically, it's pretty much exactly the same. And what a watermark is like some kind of metadata record that also has a timestamp. And when the system receives this watermark record, then the timestamp of the watermark basically tells the system that it does not have to expect any more data with a timestamp smaller than the watermark's timestamp. So this gives us basically a way to measure progress or time progress in an operator. So when an operator receives a watermark that says now it is like 12 o'clock, then we know that we can like perform all the computations that can be done up to 12 o'clock. So this is basically the way that Flink performs event time processing, and the watermarks can be used for, depending on how tightly you configure these watermarks to be produced. So like how much slack you basically give for out of order records to arrive. There's a trade-off between the latency of results. The more slack you give, then the longer it will take, or the longer Flink will wait for data to arrive, and the higher the latency for the result will be, but also the more complete the result will be. So with watermarks, you have a very, very good way of trading off result latency and result completeness.
Going back to the statefulness of the cluster, you mentioned that that's primarily maintained local to the individual processing nodes. So I'm curious how you handle cases where there might be potential conflicts in the computation across different nodes, or also how you handle the exactly once semantics in a distributed fashion with that local state management.
Yeah, sure. So first talking about the conflicts. So in Flink, all state or most of the state is always organized per key, and this is usually most of the relevant state. And for this keyed state, I said before that all the records that have the same key have to be routed to this node. So they will basically arrive in some sequential order at the node and then be processed sequentially one after the other. So there is not really any write conflict there, because they're processed one by one after the other. And if you, for instance, have a constraint that you're saying it's a distributed system, so like giving guarantees about the order is always difficult. Data is arriving from different nodes. If you would like to enforce that the changes are done in a certain sequence, then you can always accept the event, put it into state, have a look at its timestamp. So usually you want to perform the modifications based on the timestamp. And then you can, based on the watermark, when you can take out what element from the state and then apply the change. So that would be like the way how to handle conflicts. To the question of like how does Flink give exactly once guarantees for state. So this is done in Flink with its checkpointing mechanism. And a checkpoint is a consistent snapshot of the application of the whole of the data of the whole application. So this means that when the system decides to perform a checkpoint, the worker will send a notification to all the sources, so to the operators that ingest the data, and tell them, hey, I want you to perform a checkpoint. And then the source operator will record its current reading position. So for instance, if you're reading from Kafka, this would be like the reading offset in all the partitions of the operator. And then it would inject a special marker into its output. This is again a metadata record, a little bit similar to a watermark. And then this record flows downstream exactly at the same. It stays at the same position it's in the data stream. And when it is received by the next operator, then the operator will perform a copy of its own state and send the metadata record, this checkpoint barrier, to its downstream tasks. So with this checkpoint barrier mechanism, we can basically ensure that all the operators perform a checkpoint at the logically same time. So we have all the state of the we have the reading positions at the sources, and we have the state of all of the operators, and we store all of that in a distributed file system like HDFS or S3 or any persistent data store, basically. And if then something goes wrong or a failure happens, Flink restarts the application and initializes the state of all the operators, like the sources and all the processing operators, with the state that was previously checkpointed. So we basically go back to exactly the same position that we've been before and continue processing as if nothing happened. So to some extent, that is like similar as loading a saved state in a computer game. So before you enter like a tricky level or whatever, you save your current game state. Then you go into the level. If something goes wrong, you can always go back and try again. And that's basically exactly the same that Flink is doing here.
And in terms of scaling the cluster of nodes, what are some of the limiting factors in terms of the number of nodes or any sort of geographical distribution capabilities that Flink supports, and some of the factors that operators should be thinking about as they're designing the network topology and deployment topology for their Flink cluster?
Yeah, so we have our Flink. There are some Flink users who run applications on 10,000s of cores. So, like the biggest users are probably Netflix, Alibaba, and Tencent. So they're running the applications on like 10,000s of cores, as I said, with multiple terabytes of state. And these applications process trillions of events per day, which is like a couple of millions every second. In order to get to this scaling numbers, what Flink users have to do is they have to like carefully configure their checkpointing mechanism, like the how often the checkpoints are performed, what the state backend is that they want to choose. There are certain features of the checkpointing mechanism, like as asynchronous checkpointing, incremental checkpoints, and so on, that you can enable. Most Flink applications don't run across clusters, so like I haven't seen like, I mean, besides some demos, I haven't really seen like geo-distributed streaming applications being run on Flink. So in terms of like how to configure the cluster, that's a good question. Actually, I don't really have a good answer to that one.
That's totally fair. And then in terms of cluster topologies, another thing that I'm curious about is particularly for events that you might want to have either multiple execution paths or multiple uses for those particular records, if there's any support for things such as fan out and fan in for the flow of the data through the Flink cluster.
Yeah, so the programming model of Flink, or the APIs, certainly allow to like branch and merge data flows again. So in the data stream API, you have these like have an object that like denotes a data stream. You can just read multiple times from that. So if you like a data stream object, you apply multiple map functions on it, not sequentially, but like in parallel, then the API will take care of like fanning out the stream and sending it to each of the individual map operators. And then there are also like operators that can consume multiple streams. So you can then also merge these streams again together, like implement your own join logic, or just having a union operator that just unions all the events that are coming from either stream.
And going back to the cluster level, I'm curious, what are some of the failure modes that you have seen and some of the challenges that operators should be aware of in terms of being able to maintain the overall health of the cluster?
I think Flink is kind of similar then to many of the other distributed systems. So as I said, there is different kinds of failures. There you can have like a worker failure where just the worker process goes down or the worker machine goes down. This is addressed by the like regular checkpointing mechanism or checkpointing and recovery mechanism. So Flink will then bring up another worker process somewhere in the cluster, depending on what kind of like resource manager you have, or you're running on, whether you're running on Kubernetes or Yarn or Mesos, and we'll bring up a worker and restart the application and load the state into the application. If you have a master failure, that the master holds the meta information for an application in its memory. So, and if you configure Flink to be resilient also for worker failures, for master failures, then this data, this meta information is also persisted during a checkpoint, also written into a distributed file system, and then Flink puts a pointer to this data into Apache Zookeeper. So in order to have a highly available cluster, Flink is currently relying on Zookeeper. So you basically store the pointer to the meta information in Zookeeper, and then if the master node goes down, the new master only needs to know an application ID and the information how to connect to Zookeeper. So it then connects to Zookeeper, looks up the pointers to the data that needs to read from Zookeeper, fetches all the metadata, and the workers basically are restarted as in a regular failure mode. So these are roughly the failure scenarios that can happen. In terms of scaling, I said data is sharded per key in Flink applications typically. So if you get into a situation where you're running out of disk or memory space, depending on your state backend, you can always scale out. You can scale out an application basically by restarting the application with a higher parallelism, and then Flink will distribute the state is able to distribute the state to a larger number of worker nodes. So the state is then repartitioned and sent to the different worker nodes. So if you're running out of storage for your state, there's also ways to scale the application up or also down if you need fewer compute resources.
And so in terms of building and maintaining the Flink project and community, what have you found to be some of the most challenging or complicated aspects?
Yeah, so from a technical point of view, of course, correct behavior in failure cases is always a challenging thing. How to ensure that you get all the messages that you need to get, and all these classical distributed systems problems. Serialization and backwards compatibility are also tricky, especially if you have in stateful stream processing, the state of an application it might change over time, but if you often want to just keep that state, right? And if you upgrade to a Flink version, you would like to be still able to read all that state, how the data is laid out, how the serialization format is, and all these things need to be carefully designed in order to have some sort of backwards compatibility there. So these are the technical challenges. You also mentioned the community. This is, in fact, what I would say maybe even harder. Scaling a community is really hard. We're currently at the point where Flink is gaining lots of tractions. We have lots of people who would like to contribute to Flink. We're getting many contribution proposals for new features that need to be reviewed, and all of that eats up a lot of time. It's well invested time, I think, but at the same time, we at Data Artisans, we also of course have some kind of an agenda or roadmap where we would like to bring Flink, and then it's difficult to decide how to invest the time or where to invest the time, so to say. And of course, with the growing community, you also need to put somehow some kind of processes into place that reduce the effort, basically where the bottlenecks are, so to say. So you have to somehow find a way that is still convenient to contribute to the project, but at the same time also try to reduce or to streamline the reviewing and merging processes for the committers.
And in terms of the data that gets ingested and processed within Flink, is it primarily treated as just an arbitrary array of bytes, and it's up to the application logic to provide any sort of meaning or schema to it? Or does Flink have built-in support for being able to store and validate schemas and type information for the data objects that's flowing in. And I'm also curious as far as the types of serialization or file formats that are most well supported.
Flink has like support for JSON and Apache Avro, for instance. Like in looking at file formats, so Flink has a rich, like let me put it that way. Flink has a rich connector ecosystem. So we have connectors to read data from Apache Kafka, from Kinesis. We can talk to very different types of file systems. There's a JDBC connector, Cassandra, and Elasticsearch, and all of these systems have their like are either agnostic to the storage format, like in Kafka, you just get raw byte messages that you somehow need to know how you can deserialize them. Many people are using Apache Avro or JSON there, and Flink also has support for that. So within a Flink application, the API is constructed in a way that you're always dealing with Java or Scala objects, and Flink has its own type system and serializer system to serialize this data. So if you have a Pojo object that you'd like to use in your application, then Flink can either generate serializers and deserializers for this object, or you can also ask Flink to just treat it as an Avro object and then use Avro to serialize and deserialize it.
For the interface for the end users and the application developers who are trying to deploy on top of Flink, what does that process look like in terms of the way that the artifact is deployed onto the cluster and some of the lifecycle management that is available for those end users?
Yes, so Flink applications are bundled in jar files. So when you implement your application, as I said, we have APIs for Java and Scala. You compile your application into a jar file, and this jar file then there's different ways how you can bring that on the cluster and execute it. We have a command line client that you can just use from the shell. There's a web interface that you can use to upload your jar file into to the master node, to the job manager, how it's called in Flink, and then start the execution from the web interface. But there's also a REST interface that can be used to manage the full lifecycle of applications. So you can upload a jar file, you can start a job from the REST interface, you can cancel it, you can basically do all the things that you can also do with the web interface, since the web interface is just using the REST interface.
Given that Flink has been around for a while and is being picked up by more and more companies, I'm curious what you have found to be some of the most interesting or unexpected ways that it's being leveraged.
Yeah, there are actually a few fun stories to tell. So we've heard like from a company, from one of the Flink users, that they're using Flink's checkpointing feature to run an application in AWS and always migrate the application to the AWS region with the cheapest spot instance prices. So you can also use a checkpoint basically to migrate an application from one cluster to the other. So you just perform a manual checkpoint. We call that a save point in Flink. You basically get the state of the whole application. Then you can bring up a Flink cluster somewhere else, and then just load the state into that cluster, and they basically use that to always chase the cheapest spot instance prices. So obviously the application did not have like super low latency requirements, because if you keep on doing that, there's always some kind of some downtime involved in like bringing up the application somewhere else. But that was like one of the fun ways that I've seen like this checkpoint feature being used. And another cool story was when we learned from another user who had built the backend of a social network as a bunch of Flink applications connected by Kafka topics. So today, like this architectures might not be that uncommon, like having these event-driven applications, but that was like 2 years ago or so, and it was kind of like mind-blowing to see how somebody would use a stateful stream processor to build the backend of a social network.
In terms of the roadmap that you have going forward, I'm curious, what are some of the improvements or new features that you have planned that you're most excited by?
The Flink community is like always working on improving performance of checkpointing and recovery. So that is like a continuously ongoing effort. Also, the SQL or relation APIs receive lots of contributions these days. For example, we just recently received a proposal for a better integration with Apache Hype's metadata catalog. So this will basically then allow Flink to just read data that is maintained or stored in a Hive catalog. Yeah, I think an important point for Flink's long-term vision is, of course, like this complete unification of batch and stream processing, joining the APIs, the data set and the data stream API into like a common API that can be used to process bounded and unbounded streams, and also do this on the execution level. This is something that I'm really looking forward to.
And as you mentioned, with the growth of the community, there come people who are either trying to request or submit new features or capabilities or enable Flink to serve different use cases. So I'm curious if there are any of those that you've dealt with recently that you are explicitly not planning to support.
Yeah, so that's a really good question. So I haven't really seen proposals that would be that would not be in the interest of Flink yet. So I mean, of course, there have been some out. Can really recall them, but like most of the proposals are meaningful and coming from users who are running on Flink in their environments. So the tricky thing there is always like to also manage the expectations correctly and not accept too many of these proposals, or somehow be able to when you say yes, you can do that, also have like the resources to actually being able to review the changes later on. In general, I think, as said, like Flink is trying to like cover the full spectrum of stream processing applications. Something that is, I would say, Flink is currently not the best choice for is like ad hoc queries and data science, machine learning use cases. However, I would not rule out that at some point the community might also invest in that area.
At Data Artisans, one of the services that you provide to the Flink community is training. So I'm curious, in terms of people who have gone through those training sessions, if there are any common concepts or paradigms that they are particularly challenged by.
In general, like stream processing or the APIs that Flink provides for stream processing, like all these concept of what is possible with state and time, this is often requires a mind shift, so to say. So when you're coming from a background where you've like implemented somewhat stateless batch applications, and then you're moving on to work on streaming applications, like the mind shift that you don't have all the data available, that you need possibly to wait for more data or to decide when you can perform a computation. This is something that is, I would not say people are struggling with it, but it certainly requires like as I said, a mind shift. How to deal with watermarks, how to, as I said, decide when you can perform like a computation and so on.
And are there any aspects of Flink and stream processing in general that they tend to find most interesting or exciting as they're going through those trainings?
Many of the many people or many attendees of our trainings are very interested in SQL, and I guess that's also because SQL makes many things a lot easier, because when you're using SQL, you don't have to care about state. You don't have to care like that much about time. Of course, you need to like somehow keep in mind or monitor how much state your query is consuming, but you don't have to implement the handling of state. So SQL is certainly and relational and the relational APIs are certainly of very large interest for Flink users and also the people who attend the Flink training.
And are there any other aspects of Flink or stream processing or the work that you're doing at Data Artisans that we didn't cover yet, which you think we should discuss before we close out the show?
No, I think it's that was yeah. We covered most of it. Yeah.
And so, for anybody who wants to get in touch with you or follow the work that you're up to, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology for data management today.
Yeah, so something that I think is where still a bit of a gap is like unified storage for streaming and like recorded streaming data. So the goal here is basically to like store streams without retention, like and persist streams in some kind of a storage system that gives efficient read access to the historic parts and the live parts of a stream, but also like is able to make the switching point from historic to live data basically invisible for the system consuming from this data. This is important because many of the streaming applications that we're dealing with or whenever you're dealing with a stateful streaming application, it's very often the case that you would like to bootstrap the state for your application before you go on the live data. And this bootstrapping basically happens on the historic data. And in Flink right now, this is a bit of a challenge because like the batch and streaming are not fully unified yet. But it's also difficult because of like lack of support of systems that are able to provide this unified interface to record it and streaming data. There are some projects on the way to address these challenges, but from my perspective, they do not seem to have like gained much popularity yet. So one example, for instance, is Pravega, which is an open source system developed by Dell EMC, and it's exactly doing this. Like it's like an event log similar to Apache Kafka, also with providing transactional guarantees, and but it also persists the data into some kind of cold storage system where the historic data can later then be read. And Pravega has very good integration with Apache Flink. So having more systems like this available would, I think, allow for many interesting use cases.
All right. Well, thank you very much for taking the time today to join me and discuss the work that you're doing with Apache Flink. It's definitely a very interesting system and an interesting project. So I appreciate the time and effort that you put into that. So thank you again, and I hope you enjoy the rest of your day.
Yeah, thank you. Thanks for having me. It was fun.